In the previous slide, we saw how linear finite element models are built and solved by the finite element software. In this slide, we are going to see how nonlinear models are solved. Nonlinear models are solved iteratively using a Newton Raphson method. Nonlinear solutions are split into a series of linear solutions. Each linear solution is known as an iteration. Progressive solutions of a series of linear solutions provide the required nonlinear solution. This can be better explained graphically. Consider a nonlinear structure represented on a force versus deformation graph. On x-axis, we have the deformation in the structure, and on y-axis, we have the force or load. Load-deformation relationship of a structure is not linear and is represented by a curve. F applied is the applied force on the structure, and delta actual is the actual deformation in the structure. Note that we cannot write a single constant stiffness K that can represent the load deformation behavior over the entire range of loading. This model is solved iteratively. In the first iteration, stiffness of the structure K1 is calculated, considering the undeformed structure. Force F applied is applied on this undeformed structure. Assuming a linear stiffness behavior, with stiffness given by K1, the deformations in the structure, delta 1, are calculated. Note that the actual stiffness of the structure is not K1, and therefore, the solution is going to be inaccurate. Deformations delta 1 are used to calculate the new stiffness of the structure K2. Also, reaction force Fr1 in the structure, with deformations delta 1, are calculated. Note that in the nonlinear models, stiffness during the deformed state and the undeformed state are different. Therefore, reaction force does not match the applied load. This represents the error in the solution, known as a residual. In the second iteration, the additional deformation in the structure, with the modified stiffness K2, and the residual force, that is, the difference between the applied load and the reaction forces, is calculated. The calculated deformations represent the additional deformation that should be added to the structure, considering the new stiffness K2. This gives us the new deformed state of the structure, delta 2. The same process is repeated in iteration 3. New stiffness of the structure, considering the deformations, delta 2, is again calculated. Similarly, reaction forces, and the difference between the applied load and the reaction forces, or the residuals, are again calculated at the end of iteration 2. In the third iteration, a linear system is solved, considering the stiffness K3 and the residual force, to get the new incremental deformations. Adding the incremental deformations to delta 2 gives the new set of deformations, delta 3. You can see that, at the end of iteration 3, deformations in the structure, delta 3, are approximately equal to the actual deformations, delta actual. This ends our iterative solution, as we get the results that closely match the actual results. The iterative solution, in this case, is said to be converged. The iterative solution is said to be converged when residuals, that is, the applied force minus the reaction force, is close to zero, or when incremental deformation, that is, the difference between the deformations in the subsequent iterations, is close to zero.